Welcome back to Magnetic Minds, where we explore the current beneath the concepts and the circuits behind the equations. Today, we begin chapter 16, and it's all about one of the most dynamic partnerships in electronics, the RL circuit, a combination of resistance and inductance that controls how current flows over time. In this chapter, we'll explore how inductors and resistors work together in transient and steady state conditions, how to calculate time constants. If you recall, tau is equal to L divided by R, inductance divided by resistance, and understand what they mean physically, how to analyze current and voltage curves using universal exponential models, and how to apply these concepts to switching circuits, to filters, timing circuits, and a whole lot more. We'll examine the role of RL circuits in analog signal shaping, their use in digital hardware for edge control, and how they form the building blocks for more complex reactive systems. This is a chapter where energy doesn't just flow, it transforms, stores, and responds with precision. So if you've ever flipped a switch and you wondered why the current ramps up instead of jumping instantly, or if you've tried to smooth out a noisy signal, this is your chapter. Let's jump into the math, the motion, and the memory of RL circuits. I'm Professor Vasquez, and the current starts now. When we talk about RL circuits in the sinusoidal realm, not an easy word to say, we enter a space where voltage and current no longer walk in lockstep. They're not in sync. They begin to drift apart. They form what's called a phase angle between them. That's what this slide is exploring, the sinusoidal response of a series RL circuit. When you apply a sine wave to a series RL circuit, here's what happens. Voltage, denoted here by V sub S, is the source signal. Current, denoted by I, flows through both R and L, but it doesn't align exactly with V sub S, right, with the voltage source. Instead, current lags voltage because of the inductor. The lag is a phase angle somewhere between 0 and 90 degrees. And why not a full 90 degrees like a pure inductor? Because now resistance is in the mix. The resistor's voltage drop V sub R is in phase with current. The inductor's voltage drop, V sub L, leads the current by 90 degrees. And the total voltage, V sub S, is the vector sum of V sub R and V sub L. And this combination pulls the total current into a phase position that depends on the ratio of R to X sub L, so resistance to inductive reactance. So what does that mean for your circuit? So if R is large and X sub L is small, the circuit behaves more like a resistor, a small phase angle. If R is small and X sub L is large, the inductor dominates, so you have a larger phase angle. In all cases, current lags behind the source voltage, but how much depends on the circuit design. And this behavior will affect the power factor, which we'll learn about later, timing accuracy, and signal shaping. All right, welcome back. We're going to talk about RL impedance, the geometry of opposition. Again, I'm Professor Vasquez. In a series RL circuit, voltage and current are out of sync. We said that already. And the math that describes this lag is wrapped up in a powerful quantity called impedance. Let's break it down using the impedance triangle. So in AC analysis, impedance, which is represented by Z, replaces R when reactance enters the picture. So here's the idea. R is a resistance in ohms. X sub L is the inductive reactance, which introduces a phase shift. Together they form a right triangle. In this triangle, R lies in the horizontal axis, X sub L is on the vertical or the imaginary axis. That's represented by the plus JX sub L, right? The hypotenuse. Don't get me started on that hypotenuse joke. So Z is the total impedance. So if you find the phase angle theta using trigonometry, you can use the equation theta is equal to uh, inverse tangent x sub L divided by R. And you can find Z with the Pythagorean theorem. So this is why geometry is important, where Z is equal to the square root of R squared plus x sub L squared, right? All of that square rooted, right? So this triangle isn't just a drawing. It tells you the magnitude of the circuit's opposition to current, the angle by which current lags a voltage, and this matters because it lets you calculate current using Ohm's law for alternating current for AC, where I is equal to V divided by Z. Remember, Z is replacing the resistance R. So It's still the same format for Ohm's law, except for we're just using Z and instead of R. It gives you insight into power factor, again, energy loss, and resonance. And it sets the stage for solving RL circuits using phasors and complex numbers, which hopefully you've learned in your algebra class, at the end of your algebra class, or maybe at the beginning of your trig class. So whether you're working on motors, you're working on filters, or timing systems, the impedance triangle gives you the visual and mathematical framework to analyze what's going on. Solving the impedance triangle, a real example. My name is Professor Vasquez, and let's take everything we've learned about RL impedance and apply it to a real circuit example. This slide walks you through building the impedance triangle from actual component values. The given values are resistance is equal to 1.2 kiloohms. X sub L, which is the inductive impedance, is going to be 960 ohms. And from this, we'll calculate the total impedance, which is denoted by Z, and the phase angle, which is denoted by theta. Now, the first step to find Z is we use the Pythagorean theorem. Remember the formula we just covered. Z is equal to the square root of R squared plus X sub L squared. And let's go ahead and just plug and chug the numbers. I'm going to go ahead and walk you through this and make sure you can punch this in your calculator and you get these numbers right. So first, I want to change the 960 ohms to a kilo ohm value, and that's going to be 0.96 kilo ohms. And so now I can plug that into the formula that we have that we're using standard units. So Z is equal to the square root of 1.2 squared plus 0.96 squared, and all that square rooted. Remember, this is all now in kilo ohms. So Z will be equal to the square root of 1.44 plus 0.9216. You add that together, it's the square root of 2.3616, square root that, and we end up with approximately 1.54 kilo ohms. Now, this is a magnitude of impedance, the hypotenuse of your triangle. Step 2, we want to find theta. So use the inverse tangent to find the phase angle. Theta is equal to the inverse tangent of x sub L divided by R, right? X sub L divided by resistance. So theta is equal to the inverse tangent of 0.96 divided by 1.2, and this is approximately 38.7 degrees. So in polar form, we now have Z is equal to 1.54 kiloohms at an angle of 38.7 degrees. This means that the total opposition to AC is 1.54 kiloohms, and that the current lags the voltage by 38.7 degrees. Oh, I don't know why I said stuttered with the 7, by 38.7 degrees. We have a visual insight here. The impedance triangle helps us see this. It shows us that the horizontal leg, R, the resistance, is equal to 1.2 kiloohms. The vertical leg, X sub L, is equal to 960 ohms. And the hypotenuse is Z, which is equal to 1.54 kiloohms. The angle theta between them is 38.7 degrees. This graphical tool is powerful because it tells you just at a glance the magnitude of total impedance, the timing relationship between voltage and current. Phasor analysis applying Ohm's law to AC RL circuits. Hello, this is Professor Vasquez, and we're going to shift into analysis mode and apply the tool that has served us well in DC circuits, which is Ohm's law, to the world of AC and RL circuits. The only difference is we now deal with phasors, not just scalars. So in a series RL circuit, Ohm's law takes the phasor form. V is equal to I times Z. Again, remember Z is being used now as impedance, or where we calculate a resistance. So where V is the total voltage phasor, I is the current phasor, and Z is that total impedance. Again, it includes both R, resistance, and inductive reactance, which we denote by X sub L. You can also rearrange this equation just like you did in DC circuits, right? I is equal to V divided by Z, or Z is equal to V divided by I. The math may look familiar, but now the quantities carry magnitude and phase. Here's the key advantage of working in phasors, though. In a series circuit, current is the same through all components. So that means that you can calculate each voltage drop by multiplying I, the current, by each impedance value, so R or the Jx of L. You can analyze the phase shift by visualizing the voltage vectors for the resistor and inductor separately, then summing them. It's all vector math. Again, you should have learned this in at the end of your algebra course, or maybe at the beginning of your pre-cal or trig course. And we'll do a review in this course as well on phasors. But again, we're going to look at this through phasor notation. Remember that impedance is complex. So when we talk about complex numbers, right, Z is equal to R plus J X sub L. That's the form, sorry, for that complex number. So when you multiply it by I, you get both the magnitude of V, the angle of V and I, and this lets you predict and control the following: the power delivery, the voltage drops, and the phase alignment in real-time AC signals. Voltage phasors, putting numbers on the triangle. Again, this is Professor Vasquez, and now that you know how to find impedance and angle in a series RL circuit, let's take it to the next step, calculating the voltage phasors. And this slide is going to walk you through a real example using the impedance triangle from that we learned in slide 4, and it's where phasor analysis really comes alive. From our earlier triangle, right, total impedance Z was equal to 1.54 kiloohms at an angle of 38.7 degrees. Resistance R was equal to 1.2 kiloohms. Reactance, or the inductive reactance, which is denoted by X sub L, is equal to 960 ohms, or 0.96 kiloohms. So let's go ahead and assume that I is equal to 10 milliamps RMS for this example. How do we find the voltage phasors? So we can just apply Ohm's law. Remember, V is equal to I times Z in this case. So if we do this step by step, total voltage is going to be V sub S, where we have, again, looking at the formula, V is equal to I times Z, where we have 10 milliamps times 1.54 kiloohms. And so we just multiply those quantities and we end up with 15.4 volts. Again, the angle is still the same at 38.7 degrees. That's the overall voltage matching the impedance angle. So resistor voltage, or voltage across the resistor, V sub R, right? V sub R is going to be equal to 10 milliamps times the 1.2 kiloohms, because now we're just dealing with that component, not the total impedance. And that ends up being 12 volts. And that's in phase with current. There's no angle difference there. The inductor voltage, or V sub L, V sub L is equal to 10 milliamps times that 960 ohms, which is 9.6 volts. And this is leading the current by 90 degrees. These values create the voltage triangle and they mirror the impedance triangle from earlier. And this is useful because now you can visualize phase relationships. You can predict how voltage divides across R and L. You can solve RL circuits quickly using phasor multiplication instead of solving differential equations. And because current is the same everywhere in a series circuit, this method is clean, it's direct, and it's scalable. Frequency and phase, shifting the triangle with speed. In RL circuits, one of the most dynamic things you can observe is how frequency affects the phase angle. And this slide shows exactly how that plays out in real time. Let's go ahead and dive into what changes and why it changes. So in an RL circuit, the total impedance, again denoted by Z, is made up of R plus J X sub L, that's in the complex form. And X sub L is equal to 2 pi FL, so 2 times pi times frequency times inductance. And it just means that reactance increases with frequency, right? So because they're directly proportional. So what happens as frequency increases, the vertical leg of the impedance angle X sub L, that gets taller. That diagonal Z increases, and the phase angle theta also increases. That's what you're seeing in the diagram. So you have uh, Z1, theta 1 at low frequency, Z2, theta 2 at some medium frequency, and then Z3, theta 3 at some high frequency. Each triangle shares the same resistance R base, but grows upward as X sub L grows. And this matters because the phase angle theta is equal to the inverse tangent of X sub L divided by R. So as X sub L increases, theta increases. And that means that voltage leads current by a greater amount. The circuit becomes more inductive in behavior, and the power factor decreases because you have more reactive power and less real power. This is the foundation for the frequency response of RL circuits. And this has plenty of applications, like in filters, controlling what frequencies get through, tuned circuits, trying to shape responses based on frequency, and audio and RF systems, like adjusting the phase for timing and clarity. So, in short, or long story short, frequency shifts the triangle, and the triangle tells you how the circuit will behave. Phase lead and high pass behavior, the power of output placement. So you've mastered the math, the triangles, the phasors. Let's talk about the applications. So this RL configuration might look simple, but it unlocks two incredibly useful behaviors. First is phase shifting, and the second one is filtering. And here's the setup. So you've got a series RL circuit, resistor denoted by R and the inductor denoted by L that are in series. V sub in applied across the series, but here's the key. You take V sub out across the inductor. Uh, this output gives you the following. It gives you a phase lead, and it gives you a high pass filter effect. So let's go ahead and start with that phase lead. So by measuring the voltage across the inductor, you're observing the leading component of the series voltage drop. So as frequency increases, in other words, V sub L becomes more dominant, and that's because V sub L is equal to 2 times pi times frequency times inductance. Remember that there's a direct relationship there, so that increases with frequency. This results in V sub out leading V sub in with a phase angle that grows with frequency. Now for the filtering. This circuit behaves as a basic high-pass filter. At low frequencies, the inductor resists current change, so very little voltage appears across it. At high frequencies, the inductor passes change easily, so most of the voltage appears across L, and that becomes your output. So low frequencies are blocked, basically, and high frequencies pass through. And where could you use this? Well, if you want to remove a DC offset or low frequency drift, we haven't talked too much about what drift is. We'll talk more about that later. Just know that that's what it is. Uh, we can also use this to shape signals and in analog audio or radio frequency, RF. And we can also use this to provide a clean phase reference or a clock alignment in timing sensitive circuits. So just remember that simply changing the position of the output from across the inductor to across the resistor, this flips the function. And that's how much topology actually matters. Lag network filtering out the highs. Okay, so in the last slide, we saw that a series RL circuit could function as a high pass filter, and it produces a phase lead, all based on where we measure the output. Now we can go ahead and flip that script. So by simply reversing the output position, we convert the circuit into a lag network and a low pass filter. And here's how this version works. So the configuration stays the same. An AC input V sub in, right? You have a series RL circuit, but now instead of taking the output across the inductor, we take it across the resistor. And this changes the whole function of the circuit. What happens is that at low frequencies, the inductor has low reactance, the X of L, so it lets current through easily. Most of the voltage drops across R, and V sub out is approximately V sub in. At high frequencies, where X sub L increases, the inductor acts like a barrier, and the voltage drops across the inductor, not the resistor. So V sub out um, drops, and the result is a classic low-pass filter. It passes low frequencies, rejects high, and introduces a phase lag instead of the phase lead like prior. The phasor diagram and the waveform on the right illustrate V sub out lags V sub in, and the output waveform appears slightly behind the input, especially as frequency increases. This is the inverse of the phase lead seen in the high pass configuration. And this is useful if you want to smooth signals, if you want to remove high frequency noise from analog circuits, or if you want to apply delay or to attenuate fast changing edges in digital processing. So once again, output location makes all the difference. We haven't changed the components of the circuit. In fact, don't even have to change the configuration of the circuit. It just depends on where we take the output from. These things are actually happening simultaneously. So we have basically a phase lag and a phase lead, but if we're taking the output out of the inductor, it's phase lead. If we're taking it across the resistor, it's phase lag. Inductors and switching regulators, filtering fast power. So to close out our study on RL circuits, let's take a look at where these components really prove their worth, switching power supplies. This slide shows a typical application of inductors in a switch mode voltage regulator. It's one of the most efficient and widely used power conversion systems in electronics, and this is what's happening here. So we start off with unregulated DC, a transistor switch controlled by a pulse width modulator, a PWM. This chops this DC into rapid pulse streams, and that pulse enters a filter section made up of an inductor and a capacitor. The inductor smooths the current and the capacitor smooths the voltage, and the result is a clean, regulated DC output. What's the inductor doing here? Everything, right? According to Lenz's law, the inductor opposes rapid changes in current. So when the transistor switches and it toggles on and off, the inductor pushes back. It stores energy when current rises, it releases energy when current falls, and it acts as a current buffer between the noisy switching input and the smooth load output. And this is important because without the inductor, the voltage would spike and drop with every pulse. The load would see erratic, unusable power, and the circuit would be less efficient and more prone to noise. The inductor enables the whole concept of pulse width modulation by filling in those gaps between those pulses with continuous current. So this is a real world power of RL circuits, shaping the current and enforcing smooth transitions and letting high efficiency power regulation become small, fast, and reliable. Inductance, susceptance, and admittance, which is the flip side of resistance. So as we shift gears into parallel RL circuits, we need to introduce a different set of tools, ones that flip the way we think about the opposition in a circuit. So welcome to the world of conductance, susceptance, and admittance. I say those slowly because it's really hard to say them very fast. All right. So here's the problem, besides me being able to pronounce those words. In a parallel circuit, you don't sum resistances or reactances directly. You work with their reciprocals. So instead of resistance denoted by R and reactance denoted by X, we use conductance, which is denoted by G, susceptance, which is denoted by B, and admittance, which is denoted by Y. And these are the reciprocal quantities of, so for example, resistance, which is G, conductance, is equal to 1 divided by R. Inductive reactance, which is B sub L, is equal to 1 over x of L, and then impedance, which is denoted by y, is equal to 1 divided by z. So you can see the reciprocals. And let's go ahead and define these. So conductance, denoted by G, is measured in Siemens, right? Denoted by S. And it tells you how easily current flows through a resistor. Think of it as how welcoming the resistor is. Inductive susceptance, denoted by B sub L, is also measured in Siemens. It's the reciprocal of inductive reactance, and it increases as frequency increases. So the higher the B, the easier it is for AC to pass through an inductor. And then again, the last one is admittance, denoted by Y, and this is a full counterpart to impedance. Forgive my accent, people. It's a complex quantity. It combines G, it combines B, just like Z combines R and X. So then we get this new form of the complex form. Y is equal to G plus J B, right? And we use these because in parallel circuits, current divides and total admittance adds just like resistors in parallel. You add admittances, you don't add impedances here. This makes phasor analysis in parallel circuits simpler, cleaner, and it's better suited for frequency domain work. Admittance and phase, flipping the triangle for parallel RL. So in a series RL circuit, we analyze opposition using impedance, which is denoted by Z, and its triangle. But in a parallel RL circuit, the game flips. So we now work with admittance, which is the reciprocal of impedance, and its triangle is built from conductance, which is denoted by G, and inductive susceptance, which is denoted by B sub L. So in phasor form, G is plotted on the real axis, the horizontal axis, and B sub L is plotted on the negative imaginary axis because inductors cause current lag. The diagonal is the total admittance, right, denoted by Y. And yes, this forms a right triangle. So just like with impedance, but with the axis inverted. So you can use a formula for magnitude. Y is equal to the square root of G squared plus B sub L squared, right? That whole thing square rooted. And then for the phase angle, theta would be equal to negative inverse tangent of B sub L over G. So the negative sign indicates that the current leads voltage in inductive systems, or from the admittance perspective, current arrives early due to the inductive lag. And this matters because it lets you calculate total admittance just like impedance. You can solve for voltage and current in parallel AC circuits using Ohm's law, but with Y, uh, excuse me, with Y, so where you have I is equal to V times Y. Um, and if you understand how frequency affects current division between resistance and inductance, between R and L, the triangle is essential and it helps you analyze high-speed analog filters, maybe RF tuning networks, and parallel power circuits, to name a few, especially where inductive lag plays a major role. Screen admittance, a closer look at the triangle. So in this slide, we bring attention to some of the most important geometry behind parallel RL circuits, specifically how we build the admittance triangle. So let's clarify how this triangle works and what it reveals. So in a parallel RL circuit, right, G, which is a conductance, it's always plotted along the positive x-axis. B sub L, the inductive susceptance, goes through the negative y-axis. Why negative? Because the inductor causes lagging current. So their susceptance contributes to the imaginary part of the admittance, which is negative JB sub L, right? The hypotenuse of the triangle is the total admittance, which is denoted by that capital Y, and you calculate the angle theta using theta is equal to negative inverse tangent of B sub L over G. And again, the negative sign reminds us that the current leads the voltage in inductive systems, but from the admittance perspective. Remember that. So we're looking at lagging behavior reflected as a negative imaginary component. And this matters because it shows the magnitude and phase of the total admittance. It allows you to visualize frequency response in parallel circuits, and it helps you quickly assess how reactive or resistive your circuit is. So the larger the B sub L is, meaning the higher frequency, the more the admittance vector tilts downward. So it increases that leading angle between voltage and current. And to put all this together or to summarize it, uh, G is across, B sub L is down, and Y is the phasor sum pointing into the fourth quadrant with a negative angle. Complete parallel RL example, admittance in action. Again, those are my titles if you haven't realized that for each slide. So let's put our admittance triangle to work in a real world parallel RL circuit. And this slide walks us through the full solution from components to phasors. And this is how we set it up. The frequency is 10 kilohertz, that's given. The resistor is 1 kilo ohm, and the inductor, they give it to us at 25.3 millihenries. And we want to find the admittance triangle, which includes the conductance, the inductive susceptance. I'm sorry, I always like to say the denotations. Conductance denoted by G, inductive susceptance denoted by B sub L, and the total admittance denoted by that capital Y. And the first step, we want to calculate G. So G is equal to 1 divided by R. All we do is find that reciprocal. So 1 over 1.0, excuse me, kilo ohms, we end up with 1.0 millisiemens. And that's your horizontal leg. Step 2, you want to calculate B sub L. And we use the formula B sub L is equal to 1 over 2 times pi times frequency times inductance, right? So again, just a reciprocal. So you plug in your numbers, 1 over 2 times pi times 10,000 times 25.3 times 10 to the negative 3. And that's approximately 0.629 millisiemens. And this is your vertical leg. It's pointing downward, remember, because inductors produce negative susceptance. So negative JB sub L. And finally, step 3, you calculate Y. So now you want to find the magnitude of that total admittance. For Y is equal to the square root of, again, G squared plus B sub L squared, and then all that square rooted, right? And so if you plug in the numbers according to the slide, you have 1 squared plus 0.629 squared. You square root it, and you end up with approximately 1.18 millisiemens. That's your diagonal, the vector sum of the conductance and the susceptance. The math is no different from what we've done before. We're just looking at different concepts. So your triangle now looks like this. You have G, which is equal to 1.0 millisiemens in the horizontal, B sub L, which is equal to negative 0.629 millisiemens in the vertical direction, and Y, which is equal to 1.18 millisiemens, which is the hypotenuse. and that's angled down and right. And this tells you everything. How much current the circuit draws at 10 kilohertz, how much of it is in phase, like which is real, and how much is out of phase, which is reactive, and how your system is performing across frequencies. So this technique is good for high frequency analog design, AC load analysis, or anytime you want to solve parallel circuits with reactive components. Parallel RL circuit analysis. Let admittance lead the way. So we've wrapped up our admittance triangle example. Let's connect it back to our foundational tool, Ohm's law, right? Adapted for the parallel RL circuits. And this is where admittance, Y, really earns its name. In parallel AC analysis, we use phasors. So Y for admittance, V for voltage, I for current, and we apply it to Ohm's law in reciprocal forms. So admittance is equal to, admittance is equal to 1 over voltage, voltage is equal to 1 over admittance, or current is equal to voltage times admittance. Right? The last equation is the key to solving parallel RL circuits. And this is because in a parallel circuit, voltage is the same across all branches. So instead of summing voltages like we did in a series, we just multiply each branch's admittance phasor by the shared voltage, and that's going to give us the current phasor through that branch. Then you just sum the current phasors vectorially, and you get the total current. And this matters because uh, it helps you quickly solve circuits with multiple parallel impedances. You can analyze current phase relationships. You can determine how much of the current is real, again, in phase, and reactive, which is out of phase. And it keeps the math clean, especially when using admittance triangles like we did in the previous slides. So just remember this. In series circuits, the current is common, so you use impedance. In parallel circuits, voltage is common, so you use admittance. Phasors in a parallel RL circuit, admittance multiplies everything. So up until now, we've built the triangle, we've broken it into components, and now it's time to multiply by voltage and bring out the current phasors. So this is where admittance phasors show their full value. It gives us the currents that are directly in parallel circuits. So from the previous example, we had conductance is equal to 1.0 millisiemens. We had B sub L, which is equal to 0.629 millisiemens, and we had Y, which is equal to 1.18 millisiemens. Now, let's apply a 10-volt input to the parallel network. And let's do this step by step using Ohm's law for admittance. So remember, I is equal to V times Y. And so let's do the resistor branch. I sub R is equal to V times G, which is 10 volts times 1.0 millisiemens. And that's going to give us 10 milliamps. The inductor branch, I sub L, is equal to V times B sub L, which is going to give us 10 volts times 0.629 millisiemens. Again, that gives us 6.29 milliamps. And then the total current, I sub S, is going to be equal to V times Y, which is 10 volts times 1.18 millisiemens, and we end up with 11.8 milliamps. So just remember that I sub S is a phasor. It includes both the magnitude and the angle. So I sub R is in phase with the voltage. I sub L leads the voltage by 90 degrees due to the inductor. And the total current phasor I sub S is the vector sum of those two. So this confirms everything we've learned about phase relationships, admittance modeling, and that elegant symmetry of RL phasor analysis. So this is important because this technique is fast, it's clear, and it gives you one total current, it'll give you branch currents, it'll give you phase angles, and it'll give you power factor analysis in just one go. Shifts and frequency. What happens to theta as frequency increases? So to wrap up our study of parallel circuits, let's take one last look at how frequency changes, not just to magnitude, but phase angle. We always have to consider that phase angle. So we've seen this with impedance triangles before, but now let's go ahead and apply that same concept to admittance and current phasors. And the key quantities here are, remember, B sub L is equal to 1 over 2 times pi times frequency times inductance, right? 1 over 2 pi FL. And this is the inductive susceptance, the reciprocal of inductive reactance. Again, just repeating this for, I don't know. And just notice the relationship. So as frequency increases, B sub L decreases. That means that the inductor offers less current, right? So the inductive current I sub L gets smaller. And what happens to the triangle? So if we look at the phasor diagram on the slide, the horizontal axis being I sub R, the in phase component, and then the vertical axis I sub L, which is the out of phase component. So as I sub L drops, the resultant current I sub S tilts closer to I sub R. So the phase angle theta between I sub R and I sub S decreases. And what this means practically is that at low frequencies, B sub L is large and the inductor dominates. I sub S leads, and well, it leads I sub R specifically, and so you end up with a large phase angle, and then I sub S aligns more with I sub R with small phase angles, and this is the phase response of a parallel RL network. And this is important for things like analog filter design, tuning circuits, signal timing adjustments, and control systems, which you'll take later on in your program. Series parallel RL circuits. So combining opposition with strategy. So up until now, you've tackled series RL circuits, you've mastered parallel RL circuits, and now it's time to put them both together, combination circuits. And this slide introduces the series parallel RL circuits, or that combination. And this is where complexity starts to rise. But the strategy remains the same and are beautifully familiar. And this is what's happening when we're combining. You have two series, in this case, we have two series RL branches in parallel with each other, and each branch consists of a resistor and inductor in series. So one branch is yellow, right, R sub 1 plus L sub 1, and that turns into the first impedance, Z sub 1. And the other is in green there, R sub 2 plus L sub 2, and that turns into the impedance Z sub 2. So you can calculate each series impedance using, for example, Z sub 1 is equal to R sub 1 plus Jx sub L. And then the second one, Z sub 2 is equal to R sub 2 plus Jx sub L2. Then treat Z1 and Z2 as parallel branches and solve using the product over sum rule. So where Z sub T, Z total, is equal to Z sub 1 times Z sub 2 divided by Z sub 1 plus Z sub 2, product over sum. Uh, it gets a little tricky uh, because now you're working with complex numbers. So you got to be careful, right? You have to handle both the magnitude, how much opposition, and the angle, how much phase shift. And you're going to need to convert series elements to polar or rectangular form, perform complex multiplication and division, convert back to polar form if you want total impedance and phase. So there's a lot of going back and forth. And this is important because most real world circuits are not purely series or purely parallel. Actually, this is kind of fun going back and forth. Once you get really good at it and you become faster at it, it actually does become fun. So think about this. Filter sections and amplifiers, number networks and switching power supply. These are just some of the places this is important, or you'll see this in real world applications. Other things could be like RF tuning circuits with multiple branches. Again, this helps you understand how to combine RL branches in mixed configurations to allow you to control impedance across frequency or tune time delays or balance energy delivery and noise filtering. Just remember this though, solve each series branch as a complex impedance, treat those branches as parallel loads, and then use your phasor math toolbox that we discussed. Z is equal to the square root of R squared plus X squared, and then you can find the angle the same way. Theta is equal to inverse tangent of X over R, but don't forget to bring your calculator's complex model mode into play. I accidentally had my calculator in the wrong mode, and I was getting answers, but they were wrong. So make sure you're in the right mode on your calculators when you switch between going from polar to complex numbers. You'll get to know your calculator very, very well after this lesson. From voltage to power, introducing the power triangle. So you've already seen how to draw impedance and voltage phasor triangles. Let's go ahead and look at how to tie those relationships into something even more fundamental, which is power. This is where the power triangle comes in. Again, let's review real quick the example from earlier where we had that series RL circuit with R is equal to 1.2 kiloohms, X of L is equal to 960 ohms, and we had Z is equal to 1.54 kiloohms at an angle of 38.7 degrees. And then we multiplied 10 milliamp RMS current, and this gave us V sub R at 12 volts, which was in phase with current, V sub L, which is 9.6 volts, which is leading by 90 degrees, and V sub S, which is 15.4 volts at an angle of 38.7 degrees. All those voltages from the bases of the power triangle, they form a visual to help you understand how energy behaves in AC circuits. And this is important because real power, denoted by capital P here, it's tied to V sub R, the resistive drop. And then reactive power, which is denoted by Q, is tied to V sub L, that inductive drop. And then we have apparent power, which is denoted by S in this case. That's tied to the total supply voltage, V sub S. So the voltage triangle gives us the shape. If you multiply each leg by the same current, you can get the power triangle. So horizontal leg power is equal to V sub R times I. That gives us real power in watts. The vertical leg Q, that's V sub L times I, and that gives us a reactive power in VARs. And then the hypotenuse, S, that's equal to V sub S times the current, which gives us apparent power in VA, volt amps. And this is where electrical design becomes energy aware, right? You know how much power is actually used with P, how much is stored and returned with Q, and what your circuit looks like to the power source, S. So it all starts with impedance, leads to voltage phasors, and then ends in the power triangle. Power triangle complete. Watts, VARs, and VA, voltage amps. Uh, Okay, so we've traced the triangle from impedance to voltage, and now we're here with the power triangle. And this is a tool that combines magnitude, angle, and energy into one simple visual. And this is where everything comes together. So from the earlier example, we had V sub S is equal to 15.4 volts at 38.7 degrees, and then V sub R, which was equal to 12 volts. And you can also say it's at 0 degrees. If I just say 12 volts, you can assume 0 degrees. So V sub R is equal to 12 volts at 0 degrees. And then V sub L is equal to 9.6 volts. And we go ahead and apply the RMS current of 10 milliamps to each phasor, right, using power is equal to voltage times current, V times I, if you remember that. Formulas have not changed. So we multiply each voltage by 10 milliamps, we get that power triangle, or those values for the power triangle shown on the slide. Power, or apparent power, is P sub little a there. That's equal to V sub S times I, and that gives us 15.4 volts times 10 milliamps, and we end up with 154 millivolt amps. We have true power denoted by P, right? P sub true, that's going to equal to V sub R times current, which is 12 volts times 10 milliamps. That's going to give us 120 milliwatts. And then we have the reactive power denoted by Q. So P sub R is equal to V sub L times I, and that's 9.6 volts times 10 milliamps, which is 96 milli VARs. And these values are now defining your power triangle, with the horizontal leg being the real power in watts, the vertical leg being the reactive power in VARs, and our hypotenuse being the apparent power in voltamps. And this is important because true power, P sub true, is the energy delivered and consumed. P sub R is the energy stored and returned. And P sub A is the total power your system has to support. And that triangle tells you the power factor. We can calculate the power factor by the formula of cosine theta is equal to P sub true divided by P sub A. So in this case, it would be 120 divided by 154, and that gives us approximately 0.78. So a power factor of 0.78, what does that mean? That just means that only 78% of your apparent power is being converted to useful work. So it's important for sizing power supplies. It helps you manage losses and helps you tune for efficiency. If you use this, if you learn this triangle and you use this triangle, um, it'll help you in your resistance inductance journey. One that speaks not to just currents and voltages, but of what those waves are actually doing in terms of real energy. Power factor when timing becomes efficiency. So we spent the last few slides building the power triangle, and now we're going to extract the one value that power companies, data centers, and motor systems care most about, and that's the power factor. It tells you how much of the power you're drawing is being used effectively. So in any RL circuit or an RC circuit for that matter, the power factor is defined as PF, which is power factor, is equal to cosine theta. And theta is the phase angle between the voltage and current. So this simple cosine function has huge consequences. When theta is equal to zero, the power factor, so being equal to cosine zero, is going to be equal to 1. That's 100% efficiency. When theta is equal to 90, the power factor is going to be equal to cosine of 90, which is 0. And so all your power is reactive and none is doing the real work. And this matters because in industrial systems, if power factor drops too low, more current is needed for the same real power. And so this means that more heat is produced, right? You have larger heat, you're going to probably need larger transformers, you're going to have larger voltage drops, and a lot of wasted energy. And that's why facilities aim for a power factor very close to 1, typically around 0.95 or better. The graph here, it shows the cosine curve. That's between 0 and 30 degrees, and it's fairly flat. It's a small angle, and it has very minimal effect. But if you start moving past 45 degrees, the power factor drops rapidly. So let's go ahead and answer a question that's shown here in the slide. What is the power factor when the phase angle is 18 degrees? So you just plug in the numbers. Cosine 18 degrees is approximately 0.95, and that's a pretty good PF or a standard PF or an acceptable PF. And that means that you're using your power efficiently. Okay, so the final tip for all of this is it helps improve your power factor, and that means that if you want to improve your power factor, you might have to add capacitors in purely inductive systems. You can use power factor for corrections in circuits, and designing with proper load balances also helps with improved power factor. Power, the triangle that powers a grid. So we've looked at real power, we looked at reactive power, and the role of phase angle. Let's bring all those things into a single unified visual. The power triangle. So at the top of the triangle, apparent power, right? The power your utility meter sees, excuse me for my accent here, but not all of it goes to doing work. So here's how we break this down. So apparent power, denoted by S, that equals the total power that's being supplied. It's measured in volt amps, right, denoted by VA, and it consists of two parts: the true power, which equals the power that actually does work in watts, and the reactive power, Q, which equals the power that flows back and forth in VARs. The right triangle here shows us the horizontal leg, which is equal to power in watts, the vertical leg, which is equal to Q in VARs, and then the hypotenuse, which is equal to S, which is in volt amps. So just remember that cosine theta is equal to P over S, which is equal to the power factor, or the horizontal leg over the hypotenuse, if you want to look at it that way. Um, and this is important because it's what equipment must be rated to handle. Transformers must carry it, wires must support the current that goes with it, inverters and up systems must be sized for it. So even if only P is used, the system still has to carry S. And how do we improve this? With power factor correction, usually by adding parallel capacitors. So capacitors produce leading VARs, and this cancels out the lagging VARs from inductors like motors, coils, etc. So the result is you have a reduced total current, lower apparent power, higher power factor, greater efficiency. So apparent power is a total package your system carries, the real plus the reactive. So it's good to understand this so you can minimize it, and it happens to be one of the most cost-saving things that you can make in industrial power management. Just want to review some key terms that we discussed in this podcast. The first one was inductive susceptance, B sub L, and this is the ability of an inductor to permit current. The reciprocal of inductive reactance, The unit is in Siemens, denoted by S. The key term RL lag circuit, right? Resistive inductive lag circuit. So a phase shift circuit in which the output voltage taken across the resistor lags the input voltage by a specified angle. Then we have the RL lead circuit, resistive inductive lead circuit, a phase shift circuit in which the output voltage taken across the inductor leads the input voltage by a specified angle. Follow along with the quiz. Don't forget to pause the video before you hear the answer. All right, so question 1 of the quiz. In a series RL circuit, the resistance phasor is plotted along the what? A, positive real axis, B, negative real axis, C, positive imaginary axis, or D, negative imaginary axis. Go ahead and pause the video now. Okay, so if you've come back, the answer for this one is A, the positive real axis. Number 2, in a series RL circuit, there is a frequency at which the magnitude of the inductive reactance is equal to the resistance. At this frequency, the phase shift between the source voltage and the source current is what? A, 0 degrees, B, 45 degrees, C, 90 degrees, or D, 120 degrees. Go ahead and pause the video. All right, so if you're back, the correct answer for this one was B, 45 degrees. Question number 3. If you multiply each of the impedance phasors in a series RL circuit by the current, the result is the what? A, voltage phasors, B, power phasors, C, admittance phasors, or D, none of the above. Go ahead and pause the video now. All right, if you've come back, the correct answer for number 3 was A, voltage phasors. And number 4. The circuit shown is what? A, a lead network, B, a low-pass filter, C, both of the above, or D, none of the above. Go ahead and pause the video now. All right, if you're back, the correct answer for number 4 was B, a low-pass filter. Question number 5. In a series RL circuit, the phase angle can be found from the equation what? Right? A, theta is equal to the inverse tangent of x sub L over r. B, theta is equal to the inverse tangent of v sub L over v sub r. C, both of the above are correct. Or D, none of the above are correct. Go ahead and pause the video now. All right, if you're back, the correct answer here was C, both of the above are correct. Question number 6. In an RL parallel circuit, the inductive susceptance is plotted on the negative J-axis. The reason for this is that what? A, the phase angle between V sub S and I is negative 90 degrees. B, inductors are not equal components. C, current leads voltage in an inductor. Or D, all of the above. Go ahead and pause the video now. All right, if you're back, the correct answer was A. The phase angle between V sub S and I is negative 90 degrees. Question number 7. In a parallel RL circuit, the magnitude of the admittance phasor can be expressed as what? Please look at the following choices. I'm not going to read all that. A, B, C, or D. Go ahead and pause the video now. All right, if you're back, the correct answer was D. Number 8. If you increase the frequency in a parallel RL circuit, what happens? A, the total admittance will increase. B, the total current will increase. C, both A and B. Or D, none of the above. Go ahead and stop the video now. Okay, if you're back, the correct answer was D, none of the above. Question number 9. The phase angle between the source voltage and current in a parallel RL circuit will increase if what? A, the resistance is larger. B, the inductance is larger. C, both A and B. Or D, none of the above. Go ahead and stop the video now. All right, if you've returned, the correct answer is A. the resistance is larger. Question number 10. A power factor of 0 implies that the what? A. Circuit is entirely reactive. B. Reactive and true power are equal. C. Circuit is entirely resistive. Or D. Maximum power is delivered to the load. Go ahead and pause the video now. Okay, if you returned, the correct answer is A. Circuit is entirely reactive. I want to thank you for listening to this podcast. Go ahead and compare your answers from this slide to what you noted down on the previous questions. And I will see you on the next podcast lesson title.